Okay, Bismillahirrahmanirrahim. Today we are going to talk about solving minimization problem similar to maximization problem, and it's not different from maximization problem. It's same actually. You have a corner point method, and you have similar to ISO profit line method. We will have ISO cost line method, and let's say problem again. We have two brands of fertilizers available, Super Grow and Crop Quick. This field requires at least 16 pounds of nitrogen and 24 pounds of phosphate. Okay, this is the requirement for a field where we have to put these fertilizers. Super Grow costs $6 per bag and Crop Quick $3 per bag. And this is the chemical composition given in this table. Super Grow, the nitrogen is 2 pounds per bag, and Crop Quick has 4 pounds per bag, and phosphate has 4 pounds per bag and 3 pounds per bag. Crop Quick. Problem is how much of each brand to purchase to minimize the total cost of fertilizer given the following data. So this is the data here. We have the each brand, how much in each brand of bag, how much nitrogen is there and how much phosphate is there, and also the total requirement is given, and this is the cost of the bags. Okay. So it's very easy. What do you think? What are our decision variables? Huh? Bags of, number of bags of Super Grow Super Grow we have to buy, and how many number of this Crop Quick bags to buy. These are our decision variables, all right? And what do you think? Is it maximization problem or minimization?
Minimization.
It is a minimization problem. The cost has to be minimized. Minimize the total cost. And the cost of each brand is also given, right? So just define the variables. Can you do it yourself? Can you try? Quickly, please. Try. Identify the decision variables are there now. Just define the decision variables. One thing you have to note when you are writing the constraints, it says at least 16 pounds and at least 24 pounds. So this seems to be less than or equal to or greater than or equal to? Greater than or equal to constraints are there. Okay. So write down the decision variables. Let's say x1 is number of bags of Super Grow, and x2 is number of bags of Crop Quick. Then our objective function is minimize z is equal to 6x1 plus 3x2. Subject to two constraints are there, nitrogen constraint and phosphate constraint. Okay, so you can write down 2x1 plus 4x2 should be greater or equal to 16, which is 16 pounds of nitrogen, and 4x1 plus 3x2 greater or equal to 24 pounds. And the last constraint is non-negativity constraint. X1 and X2 both should be greater or equal to 0. So this is the formulation. We define the variables. X1 is equal to bags of super glue, X2 is equal to bags of Proquick. Minimize z is equal to 6x1 plus 3x2. And the model constraints are 2x1 plus 4x2 is greater or equal to 16. And 4x1 plus 3x2 is greater or equal to 24. And x1 and x2 both are greater or equal to 0. Now we can plot the constraints, okay, by making them equality. This becomes straight line equations. Alright, they become straight line equation. Draw them. For drawing a straight line equation, what do you need? Just 2 points. And the points are easy to get it on the coordinates. Okay. I think if I start teaching this, it is just a grade 10 stuff. So you should be able to do it yourself to draw these straight lines. Okay. And identify the feasible region. Identify the feasible region. Say x1 and x2. Alright, so we have x1 when x2 is equal to 0, x1 is equal to 8. So let's say this is 8 here. And when x2 is equal to 0, okay, when x1 is equal to 0, x1 is, x2 is equal to 4. So let's say this is 4. And join them together. And then we have 4x1 plus 3x2 equal to 24. When x2 is equal to 0, x1 will be equal to 6. So let's say this is 6. And when x1 is equal to 0, x2 will be equal to 8. So let's say this is double of that is 8 here. And join them. Okay. Now since these are greater or equal to constraints, these constraints are active on which side? This side or this side? Up, right? So these are active on this side and this is the feasible region. This means that the solution will lie anywhere in this region. In this region it cannot, because it will violate the constraints. And we have 3 corner points here. We have this corner point, and this corner point. What is this corner point? It is 0, 8. And this one is, this corner point is 8, 0. And for this one you have to work it out. Just multiply with 2 here. This will become 4x1 plus 8x2 equal to 32. And 4x1 plus 3x2 is equal to 24. Then we have 5x2 is equal to 8. x2 is equal to 8 over 5. which is equal to 1.6. So this is x2 is equal to 1.6, then x1, which is 2x1 plus 4 into 1.6 is equal to 16. And this will be how much? 2x1 plus 4, 6 are 24. And this will be 6.4 equal to 16. And 16, 8.4. Then x1 is equal to 9.4. 9.4. Or 8.4. 8.6 rather. 9.6. Yeah, 9.6. 9.6 divided by 2 is 4.8. These points are 1.6, 4. Huh? Something wrong? Oh, x1. I reversed it. .8 and 1.6. Alright. Then what you have to do is, with corner point method, you just work out the cost at each corner point. We have 3 corner points, work out the cost at each corner point. You have the cost function here, which is 6x1. That is equal to 6x1 plus 3x2. Put these coordinates here. The one which gives the smallest value is your solution point. Another way to do it is iso-cost line approach, which is similar to iso-profit line approach, that you have the objective function here, assume some value of z, which can be drawn within the feasible region, and then you have to move towards the region. Move towards the origin. And once you move towards the origin, the last point hit by that iso-cost line will be your solution point. Similar to iso-profit. Iso-profit, we were moving away from the origin. We draw in iso-profit line approach, we draw the iso-profit line within the feasible region and then moved away from the origin. Away from the origin, the last point hit in the feasible region, the extreme point, is your optimal point. Here it is opposite. Assume some value here, let's say 18. Okay, 6x1 plus 3x2, and then draw that. Okay, if x2 is equal to 0, x1 will be equal to 3, and if x2 if x1 equal to 0, x2 will be equal to 6. So this is not coming in the, we have to make it a bit bigger one. Assume some value here, let's say 36. Okay, then we have when x2 is equal to 0, x1 will be 6, and when x1 equal to 0, x2 will be equal to 12. So we have 12 here, which is somewhere here, 12, and this x1 6. Okay, this will be the point. Now you have to move this line towards the origin, and the last point hit will be, okay, this point is same. The last point hit will be this one. So this is your optimum. Okay, the corner point also method will do the same. So work out the cost at each corner point. Work out the cost at each point. This is the feasible rate area. This is the isocost line method here, isocost line. The last point hit is this one, where x1 is equal to 0, x2 is equal to 8, z is equal to 24. So this is the optimal minimum cost. Okay. This one is just adding the surplus variable. Similar to slack variables, we can add surplus variables with negative sign to make it equality. All right. A surplus variable is subtracted from a constraint to convert it to an equation. We had the 2x1 plus 4x2 greater or equal to 16. Okay, this was the constraint. To make it equality, we have a negative slab. Surplus variable is also called as negative slab. So this is 2x1 plus 4x2 minus s1, make it equality. Anything over and above will be subtracted from this one to make it equal to 60. Okay, so this is the standard format of writing this, especially when you are doing it in simplex method. You have to add these variables. Here, actually, this is just an introduction. In graphic approach, we don't need these surplus variables or slack variables, but to tell you that slack and surpluses can be added to make it equality constraints. Okay, a surplus variable contributes nothing to the calculated value of the objective function. Their coefficients are, in the objective function, their coefficients are 0, 0 s1 and 0 s2. So what we have is, this is the objective function, 6x1 plus 3x2 plus 0 s1 plus 0 s2. These are the two surplus variables added in the constraints, and these are the constraints here, where in the first constraint we added surplus variable with negative sign, of course, that it means subtracted from here, and 4x plus 4x, this should be 1, 4x1 plus 3x2 minus S2 is equal to 24. Okay, and these are the three corner points to work out the costs. And here we have, you can see that in this point Z is equal to 24, here at this point Z is equal to 33.6, and here Z is equal to 48. The cost is least here over here, and the surplus variable S1 is equal to 16 and S2 is equal to 0. Okay, this is the solution of with corner point method. Any questions? No questions? Is it clear?
Yes.
Okay. This I suggest that you do that. You formulate this problem. It's the Holiday Meal Turkey Ranch is considering buying 2 different brands of turkey feed and blending them to provide a good low-cost diet for its turkeys. So there is a ranch over which the turkeys are there. You want to feed them and make them fat so that you can sell them at higher price, and yet you want to minimize the cost as well. And these are the 2 brands we have. It's a diet problem. We have 2 brands here, brand 1, and in which these ingredients are there, and these ingredients should be present in these brands. Okay, they are there, 5. Okay, this is the composition of each pound of feed in ounces. Over here it is given. Please note, since this is a British system, 16 ounces is equal to 1 pound. Okay, 16 ounces is equal to 1 pound. Here in 1 pound, brand 1 has ingredient A 5 ounces, ingredient B 4 ounces, and ingredient C 0.5. And the cost per pound of brand 1 is 2 cents. Similarly, for brand 2, we have these ingredients present, and its cost is 3 cents. The monthly requirement, minimum monthly requirement for turkey in ounces is given as ingredient A is 90, B is 48, and C is 1.5. This is minimum requirement. We can have more, but this should be the minimum. Write down the constraints, and also first of all, identify the decision variables. What are the decision variables? What we have to decide? There are 2 brands, so we have how much each brand we have to buy. Okay, so we can say X1 is equal to number of pounds of brand 1, and X2 is number of pounds of brand 2. Define them. X1 and X2. Okay, after defining, what is our objective? Are we going to maximize or minimize? We have to minimize the cost. Cost per pound is given.